So firstly, I'm sorry if my voice is a bit low. I was shouting in a pub a lot last night, so and we'll see how we go. I was, a little while ago, I was writing some synthesis algorithms for Cmajor, and various people came to me and said, how do you do this stuff? Like, how do you actually manage to do some analysis of existing hardware synths and produce things that sound like it? Like, what is the techniques that you use? And I thought that'd be quite an interesting thing to try and help people with. This is really going to be quite basic in some ways, and hopefully give people some ideas about things that they might be able to do. So if we just, what I'm going to do is walk you through the process, and this is specifically about the TX81Z, which is, well, depending on who you are, either an instrument that needs no introduction or needs a little bit of background to it. So this is a famous four-operator FM synth that Yamaha introduced in 1987. Now, you have to kind of go back in time. Now, this is a few years after MIDI kind of came out, and we obviously had analog synths really as being sort of the main sort of things like, Profits and all sort of analog subtractive synthesizers. And FM was a new sort of very cool thing that came in with the DX7. And this is a sort of rack mount version of that. And it's a four-operator synth, 8 voices. And here's a picture of it. It's got stereo output. This is like exciting and novel. It's digital. There is nothing analog in this design. So that in the sense of all of the DSP, all of the processing is done in the digital domain, and then there's a DAC at the end that converts it to analog. Although we'll come into some interesting details about that later on. And it's got MIDI, which is like woohoo. That's actually very handy for us because if you're doing analysis of instruments, what you want to do is probably put some test signals through stuff, and having a reproducible way of sending notes into an instrument is very handy. And obviously MIDI is how we do things today, and it's a sort of testament to the sort of forward thinking that I can take this instrument from 30-something years ago and just plug it into my audio interface and send notes to it, and it all works nicely. If you ask why have people heard of the TX81Z, it's because of one preset. It's kind of interesting. It's called Lately Bass, and it was all the rage in sort of the early 90s for dance music and various pop songs. And it's this aspect of the instrument that I'm particularly interested in, which is FM bass instrument sounds. So you can tell a sound is popular when you can find a YouTube playlist for that one sound. There is also I discovered a Korg M1 piano playlist, which is a similar, very, very kind of popular sound. But this is the kind of the sound that I'm particularly interested in emulating from this instrument. When I was looking for pictures for these instruments, digging around on Reverb as you do, I came across this one, and it's kind of made me sort of think I should mention this in passing. These instruments are made long enough ago that typically they have linear power supplies in them, which is, we're so used these days to instruments or any piece of equipment being able to plug in America and in Europe and adjusting itself based on the voltages of the power supplies, like the power that we get out the wall. This is not like that. So this particular one, although it's listed on Reverb in the UK for a UK price, is actually a Japanese machine. It's 100 volt, 50 or 60 hertz. Japanese power is interesting in that I think half the country is at 50 hertz and half at 60, for reasons. Let's not go into that. But the key thing is, if you were to excitedly buy this instrument, plug it in the UK, smoke will come out. It won't work again, and you'll have ruined a 35-year-old instrument. Just be aware of this and be careful if you're trawling through sites looking for old instruments. So we want to emulate this instrument. Obviously, a very simple approach would be to sample it. Maybe that's what we should do. So we get our instrument, we plug it in with a MIDI lead, we get some audio out of it, and we just sample it. That's like, we're done. So what would we need to do? Well, we'd need to be able to take multiple samples per octave, because we obviously don't want the sound to go Mickey Mouse, or whatever the opposite of Mickey Mousing is when you go too far down. Don't know what the technical term for that is. If there's sustained notes, we need to put loops in and getting all the crossfading right and velocity layers. And then we would discover that we just got one instance of that sound. We wouldn't be able to jiggle controls and get any of the sort of nuance of the instrument. So it's not really a great technique for an instrument like this. So maybe that's not the right approach. So we could go the other way. We could say, well, it's, here I've got this instrument in front of you. Let's take it apart and actually really learn how it works. So we can find all the chips and, decap them and photograph them and reverse engineer the entire circuit of all of these embedded ASICs that are in the Yamaha put to this instrument 35 years ago. And then that way we could build a very, very good emulation of it. It feels like madness, right? Well, there's this guy, Ken, I'm going to say Sharif, who has done exactly this with the DX7 chips. And there's a wonderful paper, and you can go and dig around on this, his efforts of actually doing exactly this, learning exactly where all the gates are on these amazing chips that were designed all this time ago. I'm not going to go that route. I think there's a middle ground, which is probably why you're here. Although I imagine if I sort of pulled out some gear and started scraping chips, it might be quite interesting. But yeah, so let's just realise there is a continuum here, and there's different approaches. In this particular problem, I'm going to go sort of a middle ground. I'm a software engineer, so what am I going to do is I'm going to start with this basic process. I'm going to say, let's go and find out what we can about the instrument. Let's go and read manuals, do a bit of research, find out what we can to understand the building blocks that we use to put this instrument together. Although we've got all of this stuff, it isn't necessarily all used for the sounds we care about. So there's two things here. We can think of emulating the whole instrument, or we can think about doing the bits that are necessary to produce the sounds we care about from that instrument. And that's the route I'm taking here. So I'm starting with the lately based sounds, and I'm saying, which bits of this architecture are actually used to make the sound, the lately based sound? There's absolutely no point learning about and implementing bits that we're not going to ever use when we're creating these sounds. So for those parts that we've determined, work out a way of exercising them, sort of driving those parts of the architecture with test signals or test data in order to kind of get a model of what's going on, and obviously then write some software that does how we believe this works. So this is kind of a black box approach. At no point am I actually saying I'm going to find out how Yamaha did it or whoever it is. I'm going to say, let's take the concept and see what signals come out and say, can I think of an algorithm that would produce those signals? So we pull out the TX81Z manual, and it has a section. How does the TX81Z work? It's not very long, and it's unhelpful. And the reason for this is, how does the TX81Z work means two very different things. If you're a musician, it's how do you use the TX81Z? How do you actually, on stage, push buttons and make useful sounds out of it? The other, obviously, is an engineering pursuit, which is what's going on in the box. However, what it does have is a section on programming the TX81Z, which says these are all the parameters and gives you a few paragraphs on each telling you how they work. That is useful information, but the how does it work, which might seem like the obvious place to start, not the place to go. There is also this handy picture on the top of the instrument. I don't know when these things became popular, but a rack mount that has a picture that you can't see when it's in a rack. And also it tells you, this is obviously very important, I think it says the TX81 said memory construction. It tells you how the data is laid out when you save it to cassette tape. Yeah, for reasons on the top. So it's great. So it's just a graphic, I think, really. Again, unfortunately, nothing useful there. I'm going to contrast this with another synth that I really like, which is the K2000. Now, this is the musician's guide. Now, clearly by 91 or whenever this instrument came out, and the Kurzweil team, their idea of what a musician cared about was rather different from the how it works, which button to press. They've got huge amounts of detail. This book is, I don't know, 400 pages long. Each of the algorithms, each of the filters that you can use. I mean, in this case, we've got one filter displayed with frequency plots with different parameter values and a description about it's two-pole low-pass filters and blah, blah, blah. It's really, really, the engineers clearly really proud of this technology and feel that the musicians would get more out of the instrument if they understood what was going on. So this sort of gives you an idea that there are manuals that sometimes tell you an awful lot of useful information and other ones that maybe don't. So don't rule them out. Go and dig and see what you can find. So here we are. We've decided we can't really learn that much apart from what all the parameters are from the instrument. So what are we going to do? Well, you play around with it. You load the sound that you care about, and you find there's probably other bass sounds on the instrument, and you play with these and play with those and go, okay, right, fine. And then you go and look, you kind of do the edit the program. I'm going to go and change this thing. And you find what's been zeroed out, like what's off. You find which parameters, if you turn them up and down, don't seem to change the sound. This is kind of giving you like the problem space gets smaller and smaller. Each time you realize, hang on, this isn't turned on, or it's only using this oscillator or whatever it is. As you can kind of visit the sound and learn from it, you again turn this, or all these parameters down smaller and smaller and smaller. So in this case, looking at the lately bass sound, there's a whole list of things that I realized we don't care about, we're never ever going to use. Specifically, the instrument has a performance mode. If you remember back at the beginning, I said it was 8-voice and it was multi-timbral. There's all sorts of ways of, splitting keyboards and having different sound. This does not change the sound. And in actual fact, the moment that you pull this into a DAW, you are unlikely to need the built-in split keyboard sort of stuff. You would simply have multiple tracks, multiple instances, and effects. Even though the effects are switched off in this case, they're really crummy because it was difficult to do that stuff then. And you would just do that with other plugins anyway. So to make a useful thing, again, we can just go through this list and go, I don't need that, don't need that. Microtonal tuning, I mean, this is really great stuff, but I don't think anyone has probably ever used it on this instrument. So again, there's this realization that there's Yamaha designing this thing and with a team of engineers, and as we know from product development, everyone's trying to work out how to sell more of something. And they'll have gone through this list of things and said, hey, maybe this is going to move the bar for some people if we add this feature or this feature. And so there will be things in the instrument that just kind of weren't that popular. Breath controller, I was talking to somebody yesterday who said, actually, there's quite a lot of people that use that. I've never, ever seen one, but there we are. So, okay, there are people, right. But so for this particular bass sound, breath control, not important. So a whole load of features and parameters disappear, less to worry about. I said this was a 101. Now, I just want to hammer this point home. How do you test an instrument? It's got MIDI in, it's got audio out. You plug it into your computer, you stick notes in and you see what audio comes out. You record the waveforms. You don't listen with your ears when you're doing the analysis. You capture data. You have reproducible tests. It's like science, right? You put notes in, you do some analysis and you see what comes out, and you plot graphs and do this sort of stuff. Obviously, you validate these by listening, but the listening is not the way you do the analysis. It's how you prove that that your approach is correct. So, having looked at the manual, having looked at the parameters that we care about and stuff, we've got this basic idea that internally there is envelopes, oscillators, modulation, which is the whole FM thing. Because if you go through the parameters, you find this says oscillator 1, frequency, envelope 1, attack rate. So you can kind of put the building blocks in. So notice that we've taken the whole what is a TX81Z? And we've ended up with 3 bits. We need envelopes, oscillators, and modulation matrix. And then we have this question of, what is the modulation matrix? In the manual, it ends up being, I think, effectively one parameter, algorithm. And there's a little, at the beginning, there's a pull-out sheet that has, like under the synth, that has pictures of each algorithm. And I've reproduced one of them on the right there. So it has very cool little pictures. And what these are really telling you is where the signal flow is. So you've got 4 oscillators in the voice, and it's basically saying oscillator 4 modulates itself, and the output of oscillator 4 modulates oscillator 3, and 3 is modulates 2, and 2 modulates 1, and then you hear the output of oscillator 1. This could be obviously a long, thin chain, but they've done it in a little picture like that to make it fit on the graphic. So if we go back to that picture before of envelope, oscillator, modulation matrix, it could kind of be written like this. If the sound that we're interested in was the first algorithm or this particular algorithm. However, I think that's a step too far. I think leaving a modulation matrix in the implementation will give us a lot of flexibility. Otherwise, we'd need 8 copies of this, basically, with the plumbing between the oscillators kind of fixed, switch between them. It's just like, not very pretty. I'd much rather have the extra building block in the model. So although we could imagine getting away with only having to implement 2 things, 3, I think, is okay. So, FM. All these instruments, FM. Next step, what is FM? Well, you go to Wikipedia, of course, because it's always right. And it says, frequency modulation is the encoding of information in a carrier wave by varying instantaneous frequency of the wave. Okay, that probably reads okay, but it's not hugely clear. So what I've done here is just try to give you a real example. So the signal that is the carrier is at the top here. I'm representing this frequency here as the carrier, and the information I'm modulating onto it is this modulator signal. And basically what this means is the instantaneous frequency of the wave is higher when the modulator is higher and is lower when the modulator is lower. So if we look at the output at the bottom here, we can see that the frequency varies by the spacing of the number of oscillations per second. So clearly this is the highest frequency part, which corresponds to the highs of the modulator. And the slowest part of this signal corresponds to lowest part, so the minimum value for the modulator. The amount of modulation would be effectively altering how much modulation happens to the FM signal. So like how close it is to the original unmodulated signal, how deep the modulation is. So what do? We have a go at implementing this, right? Basic FM algorithm. I write in Cmajor. It's the programming language for DSP. You could write this in C++ if you were mad. Instead, you write it in Cmajor because it's much easier. Anyway, that's my pitch. That's my Cmajor pitch. I won't mention it. Well, I probably will mention it again. Anyway, what I've done here is I've tried to implement the simplest FM oscillator to kind of show these concepts. So what we have here, if we break this down, is that the FM oscillator has a modulating input, which is the thing that's going to modulate this oscillator. It has an output, which is the thing that we're listening to. There's a frequency that the oscillator runs at, and how much this modulator affects the output, the frequency of the output. And so really what we're doing is we're sitting in a loop here, we're outputting sine of phase. The phase is being incremented by the phase increment, which is the frequency that the oscillator is running at, but also, in addition, some factor of the modulation input by the modulation amount. So basically, the phase is being incremented by a constant amount based on the frequency of the oscillator, but an additional amount based on the modulator input. So, where do we go from here? We initialize a TX81Z patch by hitting the various annoying buttons on the front panel until we find the init thing, and then create basically a sine wave, and then turn on a second oscillator and turn up the modulation until it's kind of a bit obviously modulated and we're getting some obvious FM. And then here we've got a 1 kilohertz being modulated by 500 hertz signal with quite a high amount of modulation. And we get this interesting waveform out. Well, let's recreate that same situation with our C major patch and see what happens. And we get this. Carrier at the top, modulators, that's the 1 kilohertz and the 500 hertz. And then there's the FM signal. And it's wiggly like the TX81Z, but it doesn't look the same. Now, what I did was I tuned this by ear. So I turned up the amount of modulation, listening to it, until it kind of sounded like the TX81Z. And it is, it's kind of the same amount of modulation. But there's a difference here. And if you look at it, what's this FM output? It looks great. Like when the modulator is high, it's wiggly, high amounts of modulation. When the modulator is low, it's slow, low amounts of modulation. So it's doing the right thing. But the TX81Z has got a similar sort of high, wiggly, and low. This here is this sort of rising edge, just sort of stretched out. So this is a very low frequency part here, and this is a high frequency part here. And then they're not aligned with our FM algorithm, they're offset. They're actually 90 degrees offset, which is interesting. So if you see, this part here is aligned with this zero crossing, and this part here is aligned with this zero crossing, which is very interesting. So back to Wikipedia. In the section of FM, it says, also see phase modulation. And its description of phase modulation is so very clear, I'm going to read it out. It encodes a message signal as variations in the instantaneous phase of a carrier wave. Yeah. Okay, so that's clear, so I don't need to... okay, right, I'll just do a little bit of try and explain this. As before, we've got a carrier and a modulator, and this is the phase modulated output. What I want you to do is imagine the experience of a sort of a siren, like the Doppler shift you get with a siren. Imagine the modulator is the position of the siren relative to you. If it's coming towards you, the pitch goes up. So it's almost like as the modulator is, like as it's going past you, you get a higher pitch, and as it's going away from you, you get a lower pitch. So it's almost like a derivative thing. Rather than being the height of the modulator, it's the rate of change of it that is actually causing the pitch shift. So that's, okay, maybe kind of concept, you can kind of understand that. What does this mean in code terms? Well, all you have to do, there's the FM modulator on the left and the phase modulator on the right, is basically move where this modulation amount appears. So I've underlined them in yellow here. So what we're doing here is we've got exactly the same algorithm, exactly the same inputs, but instead of the modulator affecting the phase, the modulator affects the output, but not the phase. So it's the oscillator just carries on chugging on at exactly the same frequency no matter what. But what we hear, what comes out, has got that modulation in it. So it's an instantaneous shift in the phase of the output signal, not the rate of the oscillator running that is being modulated. This is what happens if you plug that same algorithm into in C major in and compare it to the TX81Z. And now suddenly we've got this match. So here's the phase modulator algorithm output and the TX81Z output. And you know, they aren't exactly the same, but you can see they are the same, if that makes sense. Yeah? It's a pretty close match. Now, you know, I could tweak this a little bit more and tweak that a little bit less. And, yeah, but that's, do you want to get that feeling that is clearly the algorithm that is being used in this instrument. Why they didn't call it phase modulation rather than FM, I don't know. There are actually really interesting technical reasons why FM isn't as good an option for a digital synth as phase modulation. As you change frequency, you have to alter the amount of modulation amount in order to keep the waveform similar. With phase modulation, you don't. So it's kind of a simpler algorithm, and it's got a very similar sound. The waveform just looks a little bit different. So, taking that previous slide, if we plot that on a graph, what we get is the top picture for our wonderful C major, you know, totally digital domain waveform from that exact scenario, and at the bottom, the TX81Z output. And look, very similar harmonics. This is great. There is, however, a lot of other cruft going on in TX81Z land. Let's highlight a few things. There's a noise floor, fairly obvious. There's mains hum, 50 hertz and 100 hertz. There's kind of, don't know what these are, bit of cruft, there's some funny spiky bits. There's clearly other stuff going on. Now, as I said before, the TX81Z is a totally digital domain instrument, but it uses a DAC. DACs in 1987 were fascinating things. They were expensive, and they were quite limited in ways that we just take for granted that everything is like 24-bit and can go to ridiculous speeds. The Yamaha instrument uses a 16-bit DAC, which is not 16-bit. It's got a 16-bit dynamic range, but it's actually only got 10 bits of resolution. So it shifts the 10 bits up and down depending on the current value. It's very clever. So I got a little picture of it. It's obviously fascinating how it works. Some people who are on the engineering side have had, oh, that's very interesting. But this is obviously a way that they got around certain cost limitations, and but they are trying to make money at this thing and sell this thing, and this is the DAC they used. So let's have a go at implementing this. Like, why not? So what we need to do? Well, we've got, here is a piece of Cmajor code. We've got an input and an output. So on the left, 1, 2, 1, 2. Am I still coming out? Sort of, no. Am I back? Okay. So on the left-hand side, I've got the way that the DAC works. We've got a quantizer, which is a thing that's, I'm still too quiet. Is it? What was that? That's the wrong slide. That's the right slide. How did that work? It hasn't changed here. That's brilliant. So can you hear me? I'm audible? Right. Okay. Great. So what we're going to do is we have a go at emulating this DAC. Now we need a quantizer, something that does this 10-bit and dynamic range thing, and we need to emulate these two, a bit of mains hum I identified, and a bit of low-pass filtering because that noise floor, we've got some white noise. If we kind of shove this all together, and this is a thrown-together implementation, and the quantizer's probably wrong, but it kind of looks like it works to me. If we do that, we get the top. We get that plot there. So that's the Cmajor code with the phase modulator and this emulation of the DAC, and at the bottom the actual instrument. So clearly this is better, right? It looks more like the original. Or is this kind of a step too far? Do you remember at that beginning I said only implement the bits that are important and leave the stuff that doesn't matter? This, I think, is in that category. This is just a part of the implementation where I think the Yamaha engineers would have preferred to have shipped a product that looked like my beautiful clean signal with this sort of massive dynamic range. They would have gone, we've nailed it. They unfortunately had to compromise bill of materials, all the rest of it, and produce the slightly shonky signal that they've got there. And I don't even know whether this is how it left the factory. This is a 30-something-year-old instrument. It's got rubbish capacitors in it, and goodness knows what's happened to it in its life. So I don't even know if I'm emulating the actual sound of the instrument or my copy of it, or it's my, the route of getting the audio into my computer. So I would suggest this is not the thing to do. So I've not done this, although I've done this, if you see what I mean. Anyway, here we are. We've got our oscillator, we've got envelopes in, modulator in, and then we've got a load of parameters. So what we need to do is kind of do some sort of analysis to work out how the other parameters work. We've got wave shapes, we've got frequencies, we've got modulation levels, feedback, blah, 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 blah. So what we're going to do is make the simplest patch possible, turn each of these parameters up and see what we can do. Firstly, waveforms. The manual has a little picture, which I said the parameters are actually quite useful, and it's got these eight pictures. They're actually slices of a sine wave shifted and moved. So W3 is W1 is the first half of W1 and the rest of it's 0. W2 is, if you look at it and squint, you can see it's actually the first quarter is the last quarter, but shifted up. So it's kind of, it's the signals are all there. So we can construct this using sine waves. So this is what we're doing in C major. Here's the wave shape function. So given a wave shape and a phase position, wave shape 1 is a sine wave. Wave shape 2 is the 4 quadrants cut and shifted and vertically moved. It's not difficult. Given the original instrument's probably a lookup table of some type, it probably makes sense that they've reused one lookup table and sort of said, how can we visit it in different ways to produce something interesting harmonically? If we then plot those wave shapes, this is actually the first 3. The top line is the oscillator coming out of the C major, and the bottom is those 3 waveforms out of the actual instrument. The shapes are kind of roughly right, but we can kind of see some interesting stuff going on. So most obviously, if we look at this wave shape here, where we've got the top half of a sine and then zeros, the bottom side we don't. We have this kind of shape. Now again, this is fairly obvious if you think about it. What we're doing at the top here is we're creating a massive DC offset. We're doing the positive half of the waveform and then zeros. So there's a DC component here. The average signal is not 0. This will upset amplifiers and burn out voice coils and speakers. This is not something you ship. You don't want your synth to do this. So typically what happens is you just have a very simple high pass filter in the circuit of the actual instrument, and we want to recreate that. So again, we can do that in software. If we put a DC blocking filter in, that is what the output suddenly looks like. So suddenly we get those shapes that we see in the original instrument. So this kind of tells us we're on the right track. It's not we aren't creating the wrong wave shapes. We just simply had some filtering issues there. So I've just shoved the DC blocking filter in the diagram as before, just to show like it would go here. We'd only have one of them. We don't need to do it per voice. We do it across the whole instrument. Okay, how do we work out how the volume control scales in order to affect the output level? We build a simple patch. We set the output level to a certain value. We send MIDI notes in. We get some audio. We do a calculation of what the decibel level is, and we just plot that. So what we do is we write a little program in C major which says, send a note on, capture a bit of audio, what's the amplitude of it, convert it to decibels, output that, and does that in a loop. And then we just step through. If you could remotely control the voltage, the parameter, I would write a program to generate and control the parameter. In this case, though, it was just easy just to hit the button and go, turn it down a bit, down a bit, down a bit, stick a few things into a spreadsheet, plot it on a graph. Here's a bit of code to generate the test signal. So this is an example of that kind of thing running. The peak level is a decibel value coming out. So at this point, we're at -7, just over -7 dBs. If we plot those on a graph, so this is a parameter that goes from 0 to 99, of course, because that's a really sensible range. I've ended up with -0.7 dBs when it's at 99. And if we plot this, we can see that there's clearly this linear relationship between the parameter and the decibel value. So this means that implementation for this is basically a linear curve. Towards the bottom, we just kind of disappear into that horrid noise floor of the original instrument. I'm just going to assume it just carries on. And then here we just say, well, this is a fairly sensible equation, which gives us this straight line, which is a pretty good match for those dots. And so then we end up with a function like this, level to gain. So take the level, multiply it by 723, subtract a bit, off you go. So this isn't rocket science, but that kind of works for this parameter. Every parameter is different. Some will be easy, some will be difficult. Feedback was... there's only 8 values, 0 to 7. I altered them. I worked out what factor of modulation would produce the same waveform, plotted them on a graph, and I didn't think the curve was a very good fit for these. I think it's kind of a bit wonky down here. So instead of, because there's only 8 values, I just had a lookup table and just said, well, there's 8 values, and depending on the parameter, use the right value. Yeah, I'm not going to try and work out any cleverer route when it's so obvious that that will be good enough. Oh, demo. So let's see if we've got this here. Hopefully is the C major patch, which is a bit loud. I'll turn it down. There's no envelope here. It's just a fixed envelope. This currently is a sine wave. There's 2 oscillators. I can change the waveform. I can change frequencies. I can change levels. Oscillator 2 is set to modulate oscillator 1. So if I turn this up, we start hearing the kind of FM bass sounds tone that you get. If we set these frequencies not being sensible multipliers, this is 0.5 and 1, we get really interesting and unmusical things. But these are the sorts of tones that came out of these instruments that do lots of FX, sort of sci-fi type noises. But they aren't kind of why I'm here. So anyway, but that's the kind of, I give you an idea of where we are. And obviously, if that floats your boat, put a load of time into that and work out how to make those sorts of noises. So, right, here we are, back to the...
Just a note, we're almost up for question time, but it's up to everybody if you want to continue or ask questions.
Right, sorry, how long? Sorry.
We've got 10 minutes left.
Okay, I'm going to rush through. Basically, I'll just go through the envelope. We've done exactly the same sort of thing. So we've done the various parameters, and we do the same sort of analysis of changing parameters and seeing what is a good fit for these. In this case, for the play a sensible long note and measure the peak time, like basically analyze the signals millisecond by millisecond and get an idea of where the curve is. There's an issue here where if you've got a high frequency, you're not going to see the peaks. You've got to be kind of a little bit careful because obviously the continuous waveform doesn't go through the peaks. It goes potentially higher than the peaks. So basically choose a frequency which is sensible, like 1 kilohertz will be fine. I just realized that no one cares about the tail of these particular bass sounds, and that just getting a 24 dB attenuation time was enough to produce the kind of exponential decay as a good enough fit. So it saves an awful lot of work. And then the other thing I was going to talk about was envelope scaling. So again, this is the sort of thing that you do, which is where you play the note harder, you get the sound output is louder. So again, I wrote a little bit of program here to exercise the instrument, play louder and louder notes and get the decibel level. This is the curves that you get from the different 8 settings. And that isn't the discrete steps in there, isn't me, that is the instrument. That's actually how it's been implemented. So there are obviously a lookup table with this many steps. They're about, I think it was 0.8 dB between each one. I'm just going to use curves through these. I don't need to produce this exact nature of these steps because I don't think it's important to the sounds I care about. Other people may feel differently about the sounds that they're trying to reproduce. The envelope itself is just do the attack phase, do the decay phase, blah, 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 blah. It's quite straightforward. Shall I skip an envelope? I might just go through and get to the end. Then we have this modulation matrix idea. To implement it in C major, I need to do a little bit of a hack. I need to introduce a delay of 1 sample because you can't have an output depend on an input that hasn't been calculated yet. So there's actually on the feedback loops here, a single sample delay. But that's the only kind of slight bodge there. And this is implemented by the modulation matrix, just saying for this algorithm, these are the connections, and for this algorithm, these are the connections. It's not difficult to do. So that worked quite well. So then we'll just get through to an actual demo of the final sounding instrument. So if I run this, hopefully, scroll up. So that's the lately based sound. I'll just quickly show you what that waveform looks like compared to the real instrument. So what I've got here is, that is a real TX81Z, and this is the emulation. So this is the waveform that we generate, and that's the original instrument. So the amplitude is a little bit off, and there's a little bit of slight difference right at the beginning of the sound. But if I were to, that's come out of my machine, not the speakers, of course, because for reasons. I can't do that. So I won't. You have to believe me, it sounds very similar. There's a slight difference in character at that first bit just because of the kind of like the bite right at the beginning. I can turn up some parameters in the instrument, in the emulated instrument, like the amount of modulation, and get very, very close to it. But this is with the parameters exactly the same as the original instrument. So there we are. That's the basic. So if I spin through some conclusions, my take home from this is spend your time doing the bits that matter. Find out which bits matter. Try and use analytical techniques for putting signals through instruments and capturing the results rather than trying to do it by ear. Do a divide and conquer approach. Split it into components that you can model separately. And you gain a huge benefit from doing that because you can reuse those components in other instruments and then do something actually unique, which is, I think, the thing you probably want to do, which is take the techniques from an existing instrument and say, hey, what would happen if a TX had 24 oscillators and had sort of, whatever filters in its feedback paths. And then you can easily do that because you've built, rather than the monolithic instrument, you've built useful building blocks that you can reuse in other DSP. So there we are. I should say you can see all of the code that I've used to generate it, and the actual instrument is on GitHub. And I will be pushing it into the Cmajor examples folder, but it's not there yet because I've forgotten to do it. There we are.